Hello, and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. We are doing something completely different today. This is quite exciting, actually, or maybe not for some people, but this is the first time we've ever recorded an Avid podcast out in the wild, so to speak. So I'm down at the Welding Institute, or TWI, in Cambridge, which is an amazing place. Came down here for a conference today and managed to get a bit of time off to one side with one of their experts, Dr. Steve Dodds. Steve is an expert in friction stir welding, and we're going to talk about the challenges to do with material joining and the opportunities for friction stir welding in particular, explain what that is and how it's relevant to the electric vehicle space. So, Steve, thanks very much for taking the time out to do this. I know it's a big day down here at the TWI with all these people on site.
Yeah, it's been a busy day, but a really good connection with the EV community today.
Yeah. So could you just tell us a bit about yourself? You know, where are you from? What's your background?
Sure. So, Steve Dodds, I head up the friction welding processes team over at Cambridge TWI, and we have a range of technologies which basically rubbing things together, which sounds very simple and can be misconstrued, but that is as simple as it needs to be described.
Right.
So how did I get into this is probably really the question. I got into this really through doing vehicle mechanics as a kid,
right,
starting off, and then messing about a little bit, but then jumping on to a forensic engineering degree over at Sheffield Hallam, which I must say was fantastic.
Yep.
And that gave you an appreciation of how things are made, but more importantly, how they fail. And if you understand how something fails, or try to understand how something fails, you have to go through a very methodical path right the way back to the raw material sometimes.
Yeah.
So what this gave me was an appreciation of all different manufacturing processes, why you choose material, design criteria, testing criteria. And that was a really interesting course over at Sheffield Hallam. I think they still run it in some guise or other. Yeah. But it was right at the time when CSI investigation was on TV and the word forensic was jumping around everywhere. But it was strictly true. It was forensic. And then from that, I was offered to do a PhD straight off the back of a BEng with Sheffield Hallam, but also working with TWI on a process called friction stir processing.
Okay.
Now, the idea of that was to selectively harden steels that you would normally throw in the oven and do exotic energy-intensive heat treatments for. But what we were looking to do was just process the very tip of the knife blade, and I'm talking industrial knives here, not dinner knives, folks, to selectively harden them and then put them straight into service without doing a full heat treatment.
Okay.
And that worked out quite well in two respects. It worked out scientifically robust, albeit not economically, but also it was successful because it led me to TWI.
Right.
And I was just looking today, I've been here for about nearly 8 years.
Wow.
Senior project leader to begin with, facing industry and talking to them about their challenges and development, and then section manager for the last 3 years or so. And
so before we kind of get into, because I think friction stir welding is fascinating, and we're going to get into that in a minute, but today's event was all about the different sort of welding technologies and how they're applicable to electric vehicle builds. And I think, you know, a lot of people will know, obviously, when you build a car, there's a lot of welds involved, there's a lot of material processing, material joining, and it's a big thing in the automotive industry anyway. But electric vehicles take that on to another level, because all of a sudden we're trying to do lots of things like join dissimilar materials, join cast parts to pressed parts. Mm-hmm. The battery pack assembly, there's the number quoted today was it 36 billion welds?
That's the estimate for how many welds we'll have to be doing a year.
And that was
if we get fully electrified.
Just in the UK?
Yeah, that's just the UK, yeah. That's taken into account all of the... well, compared to an ICE vehicle, it's a magnitude beyond. It's massive amount of welding.
So there's all these new challenges for complex material joining, and today's been really interesting hearing from vehicle manufacturers and different suppliers and looking at some of the interesting work that TWI is doing in the field. But your specialist topic is friction stir welding. And that is that's a technology that I've been aware of for a number of years now. But almost without exception, when you talk about it to two people, they're like, "What? What are you talking about?" It's not very well known. And when we think of welding, we think of heat and sort of spark and things, MIG and TIG, and generally we're using a heat source to bond material together. So first things first. What is friction stir welding?
Okay. Well, to put it into context, friction stir welding is one of around about 128 processes of joining things together we have at TWI.
Wow.
So the Welding Institute was changed to TWI because welding siloed it to the point where people didn't understand we did adhesives, we also do material, we also do NDT inspection, training, certification, the lot. It's a really broad church. So that's why we're now TWI, I think. But friction welding is, like I said earlier, in its simplest form is rubbing things together, but using the phenomenon of friction in order to generate heat locally at the joint interface. Now, the super simple version of friction welding has been with us since the 1950s or so, which was on your Moggy 1000 drive shafts. And GKN is still the company producing the most number of friction welds on the planet, producing drive shafts. And this is it's in a simplified form. This is a lathe with a hydraulic ram on the static end, pushing it into the rotating end. I'm simplifying that a lot. There is a bit more consideration to that, but it is a very industrially robust and established process. It allows for things like saw cut edges, water jet cut edges. It can stand a bit of grease because what you're doing is when you soften and plasticize those materials but never melt, what you do is you forge that original interfacial material out of the weld as a flash, they call it, as a band around the rotating parts. So that's rotary welding, and it's used for valve stems, it's used for drive shafts, it's used on turbine engines in aircrafts to hold the stacks together. People already rely on this. You don't know you're flying with something held together by a weld that was made with friction, but you are. So the advantages here is because, well, let's step back to the people who design the alloys. So someone comes along with an alloy saying, right, we're going to put all these constituents in, we're going to balance them, we're going to then perfectly heat treat it to give you the most perfect situation as we can for the microstructure, which relates directly to the properties, usually. Then someone comes along with a melting device of some description, whether it be a power beam or an arc or however else, turns it into a puddle temporarily and then lets it chaotically refreeze. Now, I'll get strung up for the simplicity of my insult of that situation by my colleagues. The majority of my colleagues around here melt things. But if you can not melt things, you're not causing as much damage to that material that you've just spent decades creating. Okay, so you don't take it into its liquid phase.
So you're getting rid of the sort of the puddle of material and all of the associated issues with heat affected zones.
Well, no, you still get a heat affected zone. You are pumping in heat and you are having transformational changes, but because you're limiting the amount, you're not putting it to the point of sensible heat which takes it to the melting point. Then you have to put more energy to actually turn it into a phase change of liquid. So there's a lot of energy goes into turning a solid into liquid. And then the rate at which it cools down as well has to be controlled or understood. So avoiding that completely and staying at around about 3/4, 4/5 of the melting temperature, or as we know, the forging temperature of a material, that's the realm that friction welding works in. Okay, so we can introduce the heat by rotating round. We can oscillate back and forth. Or the third way, which we haven't quite got to yet, but is friction stir welding, is to put two plates together, let's say in a butt or a lap formation, and then clamp them down and introduce a third body tool into that joint. Create heat by rubbing the tool by rotating it, and then allowing that heat to flow around the tool like a vortex of plasticized material before you then translate across the joint length. Now, this is not a visual conversation I'm giving very well, but we do have lots of web information on this in videos.
Because, I mean, it's quite easy to picture in your mind, I think, what for me anyway, like two round bits of metal being brought together and sort of forced into each other. But the concept of, it's almost like a milling tool, isn't it, that comes down in contact with the two work pieces, and it's spinning and there's pressure, and you get this amazing kind of transformation happens. It's almost like magic to watch.
Yeah, so this was a process invented at TWI back in 1991, patented by ourselves. We've licensed it out for the past 20 or so years. That's just expired, actually, the license, so the world is using it.
Right.
Learning some hard-fought lessons that we've got knowledge of. But essentially, what you're doing is you're taking a specifically designed tool, which, if I'm going to simplify again, looks a bit like a mechanical mushroom. So you've got a shoulder, of a larger diameter, and then in the centre of that shoulder, probing into the material, you've got a probe which has got features on it which promote plastic flow of the material around the tool. So imagine a vortex of plasticized but not melted material as a keyhole almost region being translated along a joint line. So we're not melting. That's definitely the key message I need to let you know.
And you can do some pretty nifty joins with friction stir welding, and it's actually one of the things that surprised me coming here and learning more about what you were doing was actually the number of applications where it's used already. You know, it's not a very well-known technique, but then there's examples all over the place here of things where it's an everyday item. And it's
TWI works on a very strict confidentiality, so we don't publicise what we're doing with other people, and that seems obvious. But there's a lot of product out there that you won't know that is friction stir welded together, or friction welded generally. So the Victoria line on the London Underground, the Bombardier Electrostar is friction stir welded, all of the extrusions, the full lengths. We're talking Apple iMacs, we're talking the Tesla battery tray, that's all public knowledge. So all of these sort of products are friction stir welded. Think of something more simpler, I guess, the Olympic Stadium seating, the Wembley Stadium seating is all friction stir welded together.
Oh, wow.
The whole stadium. It's a huge job. So basically where you want to down gauge, you want to take weight out, you can rely on a joint made by a friction weld to be at least, and this is a very conservative at least as well, because we always tend to overperform on this, but at least 80% of the parent material.
Right.
And with a fusion weld, I don't want to get strung up again by my colleagues again, but we usually outperform a fusion weld. Sometimes you can get 40, sometimes you can get 70% on a fusion weld, which then requires a post-weld heat treat to recover. A lot of the time when we friction weld, it serves us into the product as welded. There's not a need to post-weld heat treat. Right.
Okay. So you can. But I mean, actually, that might be my next question was going to be why would people use a friction stir weld in particular instead of a more conventional method? So you mentioned down gauging materials, so going for basically thinner materials because you've got a stronger weld, so you can do that. But are there any other particular reasons that drive people to use friction stir welding?
Yeah, sure. So because we're not putting in as much heat, the part doesn't distort as much and doesn't shrink as much. So you have a shrinking and a distortion effect. You also have residual stresses which balance out with distortion. So because we're not melting, we reduce that significantly as well. It's a marked reduction. We don't have any arc eye. You don't create an arc, which when you're in a welding shop down here, you've got black curtains around everywhere, and everybody's in a ventilated region, with curtains around them. It's basically done on a milling machine.
Right.
If we're done on a robot or on a milling machine, or we can bring the work to the part and manipulate around the part. There's no fume, there's no chance of porosity because we're not melting. It doesn't turn into a liquid, so there's no air bubbles. There's no spatter. There's no consumable as such apart from the tool, which can last up to 10 kilometres worth of welding.
Wow.
So when you put all of these things together, you suddenly think, well, hold on, this is basically a milling operation happening, where I'm doing milling quite badly because I'm burying the tool in the workpiece. But you can set up a raw piece of material on a milling machine, program it to coarse machine it, friction stir weld it on the same datum setup, and then change the tool again and finish machine it. So on one station, you can do 3 activities before it then gets taken off. So there's loads of benefits in considering it.
Yeah.
But the real sensible thing to do is always try and design your part for the welding process you're going to use.
Yeah. Yeah.
So, you can't assume that a friction weld will work if you currently laser weld it.
Right.
There's a need to contain forces. There's a need to be aware of the design nuances that, yes, sometimes it will convert quite well, but have a chat with us.
Yeah.
And we may be able to redesign the part so you get the absolute maximum out of that joint.
And it seems particularly sort of popular to use friction stir weld on, difficult to weld materials like various grades of aluminium, so in aerostructures and things like that. So what is it about friction stir welding that lends itself well to these harder to weld materials?
Yeah, so that was actually one of the biggest drivers for its development. Was Boeing were making the Delta II rocket back in the day when we first commercialized this process. And 2000 series aluminiums were very much on vogue because they're very light. However, you can only really plasma arc weld these materials, and that's a skill in itself. And then the repair technique for this is nearly non-existent.
Right.
It's a very unstable, or it was back in the day, unstable process.
Yeah.
Friction stir welding is absolutely agnostic to the aluminium grade it's dealing with, because all we have to do is take it to the forging temperature,
right,
and mechanically mix it. All we have to do, I say, making it sound super simple, but that's the goal, to get the heat in and heat out as quickly as possible to cause the least amount of thermal damage on the material. So when it comes to, yes, a 1000 and a 2000 series are going to perform very differently under that tool, because a 1000 is like margarine and a 2000 is much more resistant. Yeah. But essentially, because we're not melting, we don't have to worry about the metallurgy to an extent. Right. Obviously, we are causing damage, but
and that allows you to join different materials together that you wouldn't be able to join with a fusion weld. Yeah. So you can you use friction stir weld to join completely different materials together, or just different grades of aluminium, or what's the limitation?
There's a few ways around that. So generally, as a technology, friction welding, because it doesn't melt, if we do have an opportunity to join parts together that have different, let's stick with metallics for the moment. Let's say a steel and an aluminium. Okay. Now, there's going to be a few joining mechanisms or bonding mechanisms that are happening on that joint. So we heat it up. Obviously, the aluminium is going to soften predominantly, because that's nearest its forging temperature. If we were to take the steel to the forging temperature, the aluminium would be in a puddle on the floor. So we can only work in the forging realm of the aluminium. So we create the aluminium. We get the aluminium up to the forging temperature. I'm thinking of the example of rotary welding here because it's the simplest to imagine. Push the two bars together. Obviously, the aluminium is going to give, and the aluminium is going to be the one that folds around the steel. Then you press the brake and you stop, and you add an extra forging force on there to make sure it's fully consolidated. Now, there's a few things that are going to create that joint there. There's an atomic connection between the materials. Yeah. That'll be confused by the level of compositional difference in the alloying constituents. Yeah. But the purer the material, the greater chance you have of creating a joint there. So low alloy steel versus a 1000 series alloy would be lovely, for example. Right, yeah. There's also mechanical interlock available. So if you roughened up the surface of that steel, you can forge that aluminium on the most minute level to have a greater surface area grab onto that mechanical face that you create. Right. So what we're not doing here is getting around the fact that the laws of physics tell us that you're creating a galvanic cell, and that you're also, you're also, if you put that in an oven, how will that, if you fly it up in the air, on minus 20 degrees, and then you come back down on a runway which is, 40 degrees, there's clearly a thermal expansion difference, and you're straining the joint. So I'm not saying that we can solve the problems of physics and material inherently, but where it's appropriate and it's fit for purpose, it is possible to create very dissimilar joints.
And at a sort of simplistic level in EVs, things like where it would be hard to fusion weld something like an extruded aluminium component and a cast aluminium part, it would be very difficult to get a good weld integrity. That seems to be that kind of thing is where friction stir is being used to produce part at scale now.
Yeah, so we found that if we took a cast sample, for example, a cast coupon, and friction stir process through it.
I heard that word today a lot, a
Right,
coupon.
a coupon.
So what's a coupon?
A coupon is a representative simple sample which represents the mechanical and the compositional situation, but albeit on a much simpler, ready-to-make scale.
Okay.
So we're not making a demonstrator, we're not making a prototype, we're going way back to simple tensile tests, flat sheets together. Okay. So so what I'm talking about here is friction stir processing a cast surface.
Yeah.
Turns that surface from cast into a forging locally. That then allows you to weld more confidently on that surface if you use a fusion weld.
Right.
Because you've turned it into, the composition hasn't changed, but the integrity of the material and the way that we react when the heat's put onto it will be much more reliable than a cast structure, which might crack locally at the HA's edge and the shrinkage and all of this. Right?
Yeah.
But you're right, it also means that we can take a cast plate and a wrought plate, put them next to each other, and friction stir weld a joint between them, because we know that the weld will be definitely stronger than the cast material HAZ.
Yeah.
And we know that the joint line that we create will be forged, because that's what the process does.
Yeah. So you get really high integrity joint in, what are now becoming very important parts of electric vehicle powertrain. I mean, the battery box. That just sounds. That's the battery box. 5-minute job, throw it together.
Just make a battery box. Yeah.
But these things are, with a cylindrical cell pack, it's thousands of cells inside the pack, in a box with cooling sort of pathways and stuff in the box, supporting a huge mass. It's got to survive under a vehicle, getting bounced around in all kinds of different driving conditions. The battery enclosures are such a critical part of EV, and if you get it wrong, you're going to end up with an uncompetitive, overweight, or potentially dangerous EV. If you get it right, that serves as such a structural member of the vehicle. You've got this amazing ability to actually have the battery box serving a purpose inside the chassis of the vehicle, doing a good job. So it's a really critical part of the vehicle, and getting these joints right, and so they can survive under what are quite really, really difficult conditions has become a massive topic.
Well, we heard one of the speakers today at the event that we're at saying they didn't realise how easy it might be to forget how to make a flat floor on a car.
Yeah.
This is it's such a simple thing. Yeah, of course we can make a flat floor on an internal combustion engine vehicle, because it just has to be flat.
Yeah.
It just has to be made, and it has to be flat, and you can press that and form that and tack that together how you want. That's fine. Yeah. But you're right, when you're putting the weight on all of these in this area, and you're trying to put cooling channels, and you've got extra electronics, and you've got differential heat around the area, and then someone wants to come along and put a load of flow drills through and a load of studs to mount the batteries on, and then someone wants to sort of put a frame around the whole thing to stiffen it and put a sill and to give it watertight, or leak proof so it doesn't leak out as well. It's turned into probably the most critical part of the car in terms of structure and function.
And these things are big as well. Like that's the other. If you're manufacturing a part, I always think if you're making something quite small, it's easy to hold tight tolerances. But as you get bigger and bigger and bigger, like a structural fabrication like that, holding very tight tolerances on something that's like a couple of meters long by maybe a meter and a half wide, that's. So you're into actually manufacturing engineer nightmare territory now. Well,
if you look at the tolerances on a pressed floor plan, on a standard monocoque situation, the tolerances on there will be sort of 1 to 2 mil over the length of the car. So thereabouts. Some people make it tighter than that. Some people make it looser and just allow for flexibility and pressing it into shape afterwards or through the joining techniques. But when you imagine that you're trying to put together a set of extrusions, usually ported extrusions, to build up to 2.5 meters worth of length of vehicle with traverse welded extrusions. And you're sometimes welding them top and bottom as well, so it's a double-sided partial penetration we've seen a lot of as well. You're asking someone to weld something 14 times, and you're finding that the tolerances for the overall length and the flatness are actually tighter than the received unwelded extrusions if you put them all on the table. So you're asking the process to straighten up a part effectively.
Yeah, you kind of take these floppy bits and put it together and have something that's stiff and incredibly flat. And I think so. Just if anyone is now sitting there thinking, why does it matter if a battery is flat and what the shape of it is? Basically, we come back to we've got packaging up this big massive cells, battery cells, which are things that we have to handle quite carefully. We don't want them rattling around inside the battery box. We've got to get heat out of them. We have to connect them safely to the high voltage electrical system. So it's really important that the enclosure that they're mounted in is structurally sound, and we've got a good mounting tolerance there so that we can keep all the bits safe and keep the high voltage conductors away from things they're not meant to be touching. And it's a really key part of the process. And I think actually a lot of OEMs have struggled when they've been developing vehicles to get to grips with the battery production. And it also partly drives the variance in the different cell technologies. So some people would use cylindricals or pouch cells or even prismatics because it makes it easier to manufacture the battery tray, but then there are other trade-offs. So we kind of gone really deep on the friction stir welding of the battery tray itself, but it's such an important part of the vehicle, and we think it's. I don't know. Do you find it frustrating when people talk about batteries that everyone gets carried away about cell chemistry and it's all about that, but you got to put the thing together?
I wouldn't say frustrated because each part of the conversation needs considering. So the problem that we've seen today from a lot of the speakers is challenge. I'll say challenge.
Yeah.
But really, it's a problem.
Okay.
And the challenge is engineering. The problem is real. The problem is that we need to make lots and lots of welds very quickly. And we don't really want humans involved. We want to put a battery into a laser cell normally.
Yeah.
We want to close the door, and within half a second, you want 50 welds to be done. And we can make 50 welds in half a second. It's possible with remote laser. But the problem that you have with that is you have to assure that you've got very good intimacy between the parts that you're putting together, and the tooling is quite complex. Because if you've got a slight gap between very thin materials that are lapped together, what the laser blows through the top one, and it blows the material through to the air gap, and then you lose your beam momentum, if you like, in order to clip into your bottom sheet.
So this is, again, visually, where you have lots of battery cells, you have a bus bar conductor that carries the current between the individual cells in the battery pack. Those conductors are quite unwieldy. They've got to be conductive. They're normally thin metal. So we were talking about manufacturing tolerances before. You're trying to get basically a big floppy bit of metal in exactly the right place to connect.
In 50 exactly right places.
All at the same time.
All at the same time for half a second, because you don't want your tooling to be slower than your welding process, or at least slow enough for you not to consider the process. So there's a challenge using power beam. With the friction techniques, what we're looking to do is, because we have to apply force in order to create friction, well, that actually takes away one of the tooling challenges, because it means that you can have non-intimacy between your parts until you make the weld, which then presses the two sheets together and creates the weld, and then off it goes again, and they stay where they were put.
Yeah.
Okay, so there's an opportunity here for using friction. And there's the opportunity to put down a multi-head gantry system, if you like, on top of a battery, and within half a second again zap them all with friction. So this is where we're asking people to look with us. We've got a few ideas.
Right.
We've proved that we can weld aluminium to copper. We've proved that we can do foil welding in 0.2 of a second on a single head. Yeah. It's about scaling that up and seeing what it could do for simplifying tooling.
And I'm not sure if, so this is, I haven't scripted this interview, we're just sitting down and kind of chatting away, but so stop me if we're not allowed to talk about it, because I'm not sure, because in your labs today we saw a really interesting friction stir process, which was like, I can't remember what the the name was, but essentially forming like a rivet type joint. So it was a replacement for rivets in things like aerospace. So you had a very complex tool that was rotating, and you were deforming and then pushing parts back in. What's the proper name for that? Because I've not done it justice at all.
There's a long name for it, but it needs to be a bit quirkier. It's refill, friction stir, spot welding. Okay, and if I could ask people just to Google that, because I'm going to try and do a vocal description of it now, and it won't do it service. But essentially, what we're able to do is imagine a lap sheet scenario. You come in with a C-frame robot, similar to a resistance spot welder, but on the bottom side you've got your anvil, and on the top side you've got a tool coming down which clamps the sheets together. Yeah. Now within that clamp on the top side, you've got the two elements of a friction stir tool. So remember the mushroom I was talking about earlier? Right. Imagine if you had the shoulder and the probe were able to move independently vertically, but they rotated at the same speed. Yeah. And you had the ability to pull that probe in and out of that shoulder, or up and down through the center of that shoulder. Right. So what we do is we drive a shoulder and the probe onto the work surface. We don't plunge at that point. We just precondition and get a friction coupling. Yeah. Then what we do is we push down the shoulder, the annulus, into the lap sheets, and we just click over halfway, so just through into the second sheet. Yeah. The material that you would normally see displaced out the side of the tool, well, we contain that with a clamp around the outside, and the material actually gets forced up inside the tool where you've lifted the probe and created a cavity for it to flow up. Yeah. Right, you're still nodding. I'm following you. So you're now halfway through the process. I have the advantage. Right? I was watching it with amazement earlier. So we've made a good video on this because it's worth visualizing. So we're halfway through the process, right? Yeah. So then what you do is you simply reverse the motion. You pull your shoulder back out, but you lead it with a forging force from the probe pushing back down again. So you re-inject or reforge. Or you forge the material back into the hole that you've just created, or the partial pocket hole. You hold it then for another quarter of a second once the machine stopped rotating, and then you release the clamp. So what we've done there is we've created a solid state joint between two lap sheets, where you've got the properties of a forged microstructure where the joint is. Yeah. You've done it between 0.2 of a second and about 8 seconds. Yeah. And there's quite a range there, and the reason for that is it depends on the alloy, it depends on the thickness, but the thinner and the softer the alloy, the quicker we can make a weld. What you haven't done, and this is why aerospace love it, is you haven't drilled a hole. Yeah. You haven't then deburred it. Yeah. You haven't then put your sealant in at that point and committed to the fabrication that you're going to make, because you can only put so many rivets in before the glue goes off. Yeah. You then haven't put in the rivet and had to do all of the fastening and check that it was, secured in properly. You might then even have to dress that rivet back. You might have to linish it back or grind it back and then fill it up. You don't have to do that. So within 2 seconds ish, let's say, on a 6000 series 1.2 mil sheet ish, you've not done any of that. A perfect spot joint. Yeah, and it's turns out it's got all the benefits of a standard friction weld, which is that 80% is still holding about true to the parent material. The failure mode that we get is a pull-out, a nugget pull-out, which means that the weld was stronger than the HAZ around it, which is great news. That's the best you can ask for in that situation. And we've compared it to a Class A automotive resistance spot weld, and it's beaten it in terms of strength. Now, I can't say the actual numbers on this because this is within TWI membership privy, but you can imagine aerospace love this. Yeah. And they're looking very deeply into this. Automotive not so much, because automotive tend to buy solutions that are quite mature, whereas aerospace have the appetite and the space and budget usually to develop things early stage. And that's a really new sort of development of the friction stir process. It's one of the adaptations that's happened over the past 25 years. Right. Saying it's new isn't actually that true. Okay. The recent generation machines, I think, we run a Kawasaki system here, but there's a few. There's Harms and Vendor, and there's many companies around the world now that are making these systems. Yeah. But the control level now and the accuracy of these machines is just phenomenal. Yeah. And it's almost brought another level of parameters. The amount of control you've got It's a wonderful bit of kit.
Yeah.
Yeah.
And there's you've got the normal kind of linear, actually the really simple, but that again,
sorry if I'm
massive disservice.
Confusing this.
We've got the really the common, let's say, rotary friction welds that are attaching things like drive shafts together.
Axiosymmetry, round parts, they rotate them together. Yeah.
Yeah. We've got linear joining big lumps together. So there's the sort of different class. We've then got the linear tool friction stir welds, where you're creating very long welds in items, and then this other method of creating effectively these really high integrity spots.
Local spot joining technique, yeah.
And then there was one other friction technique which we saw today, which involves creating channels.
Right.
That's
right. Now you're on the edge. Okay. So come and have a chat with TWI is what I'd say. If none of this is making sense, come and have a chat with us. We've got very clear explanations. The vast majority of my job is educating people, by the way.
Well, you're educating me now. Everyone can probably tell I'm learning like a huge amount.
I'm just concerned because in front of you I'm moving my arms and you're seeing what I'm gesticulating, but on a podcast it might not come across. But I've got a face for podcasts, so that's okay.
What we'll do is we will put some links in the show notes. So people scroll down into the show notes. We'll put links through into some of the videos and back to the TWI website, so people can kind of have a look at the videos of these things. And we'll make that really easy for you to find them by putting links in the show notes below.
Yeah, that's useful. So, right, what you've just talked about is the latest sort of it's the latest avenue that we've discovered at TWI. So, the friction stir welding process is what it's based upon, and imagine if you're for some reason your machinist put in the wrong G code and he spun the tool the wrong way. So this tool that I was talking about, this mushroom I'll keep going back to, it has Fluted Designs which are designed with the rotation direction of the tool.
Yeah.
So over in Europe and this part of the world, we always rotate clockwise, so the tools are always. Surprisingly, our American friends rotate counterclockwise, so all their tools are completely different, so be aware of that, everybody.
Okay.
There is no convention, but where they can break the rules, they do.
Yeah.
So if you were to turn a clockwise tool in an anti-clockwise direction whilst you still had a forging temperature and that plastic vortex, what you'll do is you'll convey material upwards like an Archimedes screw.
Right.
Okay. Now, if that was to then go along a joint line, what you would find is you would have what we call a wormhole defect. And this but it's not scientifically wormhole. It is actually just a.
We don't get to go to another dimension.
No, certainly not. No,
okay.
It is just a continuing void usually on one side of the weld because of the way that the pressures are balanced.
Yeah.
And it runs from the very start of the weld, and when you get to the end and you pull your tool out and you see the sort of exit region of the tool, you can see a tunnel in that exit region which we know runs all the way through to the start of the weld.
Yeah.
Because someone's made a mistake, right? So this
was that how it was first found, or were you deliberately looking?
Well, it's probably an optimist who saw a defect and said, "Well, this is something we can use." So what we did is we called it a defect, but then we started exaggerating it and trying to control it and make use of it.
Right.
Now, this was done before. People use the technique to make what. And we did as well, quite rough channels.
Yeah.
So I'm now talking about a channel here. I've gone from wormhole to channel. So this is channel makes it sound more deliberate.
You traverse the two. Okay, we will put a link to the video in the show notes. But you've got to imagine these the friction stir tool traversing along a workpiece. You end up with a surface. You can see where the tool has been on the surface, but underneath you're creating a channel. So basically like a tube. You're effectively friction stir welding a tube into a solid piece of material.
Yeah. So by exaggerating the defect and by changing the tool design, the parameters to deliberately create a void, what we're effectively doing is subsurface machining.
Yeah.
Whilst keeping the lid on.
Yeah.
So that's kind of it, isn't it? If you imagine approaching from one side with a milling machine, plunging a tool into that workpiece and doing a serpentine path.
Yep.
When you take your tool out, you've got a fully closed network of fluid channels, if you like. Couldn't be fluid, could be fluid within the structure of that plate. So it's not something we can design for at the moment. It's a completely new, novel way of manufacturing.
Yeah.
It's not. No one's designing for it because no one knows what it is.
And this is this is really exciting application because people who listen to the podcast regularly will know I often talk about thermal management and the big challenges with EV. So progression in EV technology is all about thermal management. So getting the heat out of the motors, the electronics, the battery systems, caused by ohmic heating in those components from the currents flowing through them. So thermal management is one of the sort of accepted big challenges with any EVs, particularly when you're pushing the performance boundaries. And if you look at things like motor housings, or even if you look at take apart a battery enclosure, you've got some pretty complex tube fabrications or cast parts with fabricated bits on them to create cooling pathways, or even like really sexy materials like Inconel, with over-molded, overcast aluminium on the top, like really, really complex structures to make these cold plates. And it's a whole industry, brazed cool plates, fin structures, like very, very, lots of technology, lots of complex manufacturing processes and cost. And here we've got potentially this really amazing production method where you can effectively machine a hole underneath a completely sealed surface and create an intricate cooling structure without the need for some of the other processing technologies.
Yeah, so we're trying to do it in a one-stop shop, really. We're trying to on the milling machine, and it can be robotic. We can put this on as an end effector on a robot and go around 3D parts, but we're effectively trying to. If you were to make a heat exchanger now, you would have to take a plate, you would have to bury a channel into there, cut it out, you'd have to put a lap region to receive an inserted plate, which you then reseal back up with another weld. So, there's quite a lot. We showed today the cost of that and the time it takes to do that. So what we're trying to do now with this technology is move it from aluminium and move it into the copper.
Okay, yeah.
Move it into steel. Yeah. Move it into titanium. Now, the reasons that you'd go to those materials aren't because you want to make a heat exchanger for an electric vehicle. Yeah. The reason you go into there is because you might want to use, let's say for steel, you might want to put cooling channels in your carbon fibre moulds. Right. Or you might want to put channels inside titanium so you can blow form it. Yeah. Superplastically deform it for space applications, for example. Yeah. So the ability to put effectively what we used to do with a gun drill, but do it in a much more, eloquent way of a 2D or 3D motion path. Don't get me wrong, we're at the early stages. We're working on about TRL 3 or 4 at the moment in aluminium. Yeah. But we've made demonstrators and we've pressure tested them and we've leak tested them and it looks fantastic. And the channels are starting to get really uniform as well, both at the start and at the end, at the end of the process. The one thing we haven't mentioned about this, though, is the byproduct isn't swarf. The byproduct is extruded wire.
Oh, really?
Yeah, okay. So it squirts out a wire. We're actually creating extrusion, a local extrusion underneath the tool. So we push it through a die at the end and it comes out as a wire. Okay. So you get a nice, very... Well, you get a product, not a byproduct.
Yeah.
so when the additive manufacturing world are looking for low volume of research wire, and they've got the plate or they've got the tube, but they can't get the wire because no one will turn it into wire for them on such a low batch, they come to us and we make wire for people who can't obtain wire of a certain grade in such a low volume.
Oh wow! You're giving a product to your fusion welding colleagues?
That's exactly what we're doing at the moment without too much detail.
Conflicts you a little bit.
There's certain aluminium alloys that there's plenty of stock made in the last 10 years, but no one's making it currently. Right. And they think it'd be very beneficial to use it for wire arc additive manufacturing. Wow. So we're supplying our colleagues down the road there with with very rare wire.
Yeah. So I think basically, people listening, hopefully, like friction stir welding is it's an old process, but it's not one that is generally well known unless you're a proper welding boffin or expert.
Thank you.
Obviously, like you are.
No, boffin's good.
It's got some really, really interesting uses. So from sort of things like drive shafts that are in common use in valve stems, through to battery trays, and even creating cooling channels and all sorts of other places where potentially you can use friction stir welds or friction welds to create high integrity joints. In the very big challenge that we've got with EVs in terms of creating safe and repeatable and cost-effective components to go into the EV, it's a big part of the solution. You've got some people who are recognized market leaders. So Tesla, you mentioned earlier, it's known that they use friction stir weld in parts of their battery trays. So
yeah, well, they also then move that onto SpaceX. So
wow,
the standard way of making a rocket fuel tank now, and across any of the major space agencies, is to friction stir weld. Every launch that you've seen since around about 1998, those rockets have been rubbed together.
Wow. Okay. So I was just about to ask you if there was any other interesting applications. Is there anything else on an EV you think? Because there's we haven't talked about motors particularly and wire joining and things like that. But are there other areas on an EV where you think there's potential to use your technologies to improve production processes?
Well, just as a general comment, if you're welding something currently and you can take weight out, or you will need to take weight out, which is a massive driver, then consider how you might be able to use friction welding generally.
Right. Yeah.
But specifically, we're actually looking at the charging networks, because they need to make quite a lot of aluminium to copper high tension joints, and rotary friction welding is a fantastic way of joining aluminium to copper together. Right. So that's one thing that we're currently looking at. In terms of other parts around the EV, I think what I'd probably say is, rather than just try and give out cases or information, because I might be stepping into sensitive things that we're talking to people about, what I'd say is,
we'll keep the legal bots away from the cutting table.
What I'd probably say is, if you're considering putting together a design of something, and you know what materials you want to use, but you don't know if you can, because you don't know if they'll actually stay together somehow. Yeah. That's probably the point where you should think, well, can I friction weld them together? Yeah. What can stick together with a friction weld, and how is it fit for purpose for what I want? Yeah. So I'm not gonna shoot too far down because I think I've exhausted what I can say. Yeah. But there's a lot of application. And of course, so obviously TWI is the place to come if you want to learn about friction welding, and you don't just work. You have, so how many members are there of TWI? There's about 700 industrial members, right. And that means with parent companies, that's about 3,000 actual companies or sites, if you like, that we serve. Yeah.
So TWI works with membership on research. It collaborates with industrial companies in terms of doing government-funded research. So these guys, I mean, it's blown me away. This is the second time I've been here. We've seen completely different things again compared to the first time I was here. It's an amazing place in Cambridge. It's really fantastic guys who just the absolute world experts in joining. So I was going to say welding, but joining things together.
I've done my job.
You have, yeah. You done your job, and you can glue it, you can screw it, you can weld it. These are the guys who really know that, and friction, and particularly friction stir, really kind of underused method, which has got a huge amount of potential for some really interesting applications in the EV space. So. So thanks Steve for taking the time out to do this. We've kind of
for coming down.
Snuck away into a quiet little corner at TWI. I really hope everyone listening has got some value out of this podcast, and I know I've learned a huge amount. So thank you for taking the time out to listen to us today. Don't forget to subscribe, leave a comment, send us a question. We do have some episodes coming which are listener questions. So there's to be honest, some really tough questions come in recently that it's taking. We're pulling some episodes together on. So there's some interesting stuff coming there. We've got some fantastic interviews coming as well with some more experts in the field. So don't forget to subscribe, leave a comment, give us a rating. For the show, it really helps us. It helps more people see it through the way the algorithms work in the podcast channels. So thanks very much for doing that, and I look forward to speaking to you again soon.